Hello, I'm Satoshi Nakamaru, came from Keio University in Japan. Today we introduce our new sensor device, so named FoamSense. So here we use the word soft, it means mechanically soft stuff. So, soft sensors expand user experiences in HCI fields. Softness does not disturb haptic sensation of the materials, so it allows us a more haptic-rich experience. And at the same time, soft material has a degree of freedom, so it gives us to make new interface device, such as bending or pinching or twisting and so on. So there are already many research for detecting the soft object deformations. Sugiura et al. Developed the they used photoreflectors for detecting the deformation of the soft object. So they detect the light intensity and calculated how it deformed. So it is a very good solution, but the limitation is still hard component is inside in the soft objects. And in the field of the material science, there are many examples of the resistibility change materials. However, most cases, they require special chemical synthesizing process. So it is not easy for HCI researchers to access this technique. And they mainly focusing on the simple pressure sensing. I think it limits the application area. So the right picture shows the device. It made of the liquid metal and elastomers. So these materials are incompressible, so the cross-sectional area deforms in response to the external pressures. So it causes a resistibility change of the materials. So they succeed to measure the deformation, not only pressure, but also shear or bend. But the problem is safety assurance against the leakage is very challenging. So here, our target is develop the new soft sensors that can measure various deformation, so such as bending, twisting, and so on. So, but we only use soft materials and safe materials, and with very simple fabrication method. At first, please see this movie. So this sensor is we call the FoamSense. Now you can see the very soft device. So this is a principle. So when we deform the materials, the structure is changing in reaction to the external force. The red part shows the density is increasing. So now it's a kind of resistive sensors. So now we can show the demonstration. Many kinds of the deformation is led by the resistibility change of the soft object. So bend and twist and shear is demonstrated. So we mainly use two materials. One is a kind of porous materials, such as a sponge or a cotton. So it has a space inside the object. So we add the conductivity by using conductive ink. So this is a manufacturing process. Now we are shaping the soft materials and directly dip into the conductive ink. So after dry it up, so this material now it's a conductive. And we add the external wire on the surface. So this black paste is a kind of the conductive glue. So now two wire is attached both sides, and center part, the green cubic, is a kind of resistive sensor. So this is application examples. Now we put this device into the door arm. So now it works as a bending sensors. So we can get the continuous deformation. And now we put this device on the neck pillows. She can control the music on her neck movement. Yeah, this is a summary of this project. So yeah, I review the process. So at first, we prepare the two materials. One is a porous object, and the other is conductive ink. And we add the conductivity by dipping these materials and attach the external wires. So these are our contributions. First, we develop the new sensors and summarize their design process. And we evaluate many kinds of the FoamSense. So, and third, we demonstrated the FoamSense made by 3D printer, and it can show the unique property. So it shows the potential for expanding the applications. And finally, we demonstrated 3 prototypes and scenarios. So this is a design process of the FoamSense. At first, designers define what sensor mode do they want to use and what is the shape. So after that, users should choose the proper materials. Materials is one is carrier structures, sponge type or fibrous type or bead type and so on. And they need to choose a proper ink. So after that, they implement these inks into the carrier. So now I will explain later. So in some cases they dipped a whole structure. In some cases they make the patterning of the ink, and they attach the wires. This is a whole process. So at first, I like to explain the basic characteristic of the FoamSense. So now we put the FoamSense between the 2 electrodes, and we measure the resistibility, and we control the position. So now this graph shows the compressibility versus normalized resistibilities. You can see in small deformation part, resistibility decreased very radically. It means that in this region, so structure change is very drastic. But after 100 compression, so it's relatively stable. It means insulator part, I mean a hole is already compressed. So in this part, sensor devices property is almost linear. So this is a picture we captured by 3D optical microscope. You can see in a small compression level, you can see the whole structure is changing. But after we compress the largely, so almost all pore is already disappeared. So now I showed the data of the sponge, but we can also use many kinds of porous materials. So sponge and fibrous structure and beads. So we mainly use a sponge because it's a relatively homogeneous and easy to make a shape. We can cut, or sometimes we can use the mold. So, but in case of using the fibrous or beads, so we need to cutting by ourselves. In that case, we need to prepare a special case and pack this material into the case. So it is depends on the purpose. So today I mainly talk about the sponge type FoamSense. So this data demonstrated how we can get the various deformation mode. The important thing is to design the wires so as to sandwich the part where the material is compressed against the deformations. So the red part indicates the most compressed part in react to the external force. So we are carefully designed to sandwich this part. So as a result, we can detect the bend and twist and shear motions. So this is the basic function of the FoamSense. And from now, I introduce the patterning technique. So ink patterning is a differ from this research. Patterning technique is special for this research. So many material research is mainly they are using homogeneous materials. But in case we we use a patterning technique, we can suppress the ink consumption. It means more cost-effective method. And second, it is also suppress the mechanical property change. So after dipping the conductive ink, so soft object property is a bit changing. But if we only dipped on the surface areas, so internal area is original materials. So therefore, it is useful to keep original properties. And third one is we can introduce multiple sensors into one carrier. So this is an example. So sponge is soaked in different type of conductive ink. And finally, we can get the sensor device shown in the right figures. So now, left and right side, we have two pressure sensors. So it is a kind of surface. We can use this device. It's a kind of a surface tilt sensors. So this is one example of the patterning. And I also introduce other approach using digital fabrications. So in case we use a digital fabrication, so we can print out many kinds of sponge, not only cubic. So we can design by ourselves. And we can also control the position of the holes. So it means that we need not patterning by ourselves. We can control the hole positions and soak all materials into the ink. Only hole part is the conductivities. And we can also control the holes. So why we need control the holes? So I can show the example. So left picture is a sponge we printed out by 3D printers. The material is a silicone. So it's a very elastic. So and the left picture is center picture is a sponge. It has a sphere hole structures, and right picture shows it has a hole with ellipsoid hole structures. So if we make this kind of two-type FoamSense, it has different properties, both mechanical and electrical. So you can see the difference between two types of the FoamSense. So in an ellipsoid, a sphere has an anisotropic effect. So of course it's normal in mechanically, but you can see the conductivity is almost constant in one direction. So it means that ellipsoid is already a very small size. So if we push on shorter lengths, so whole structure changes a little. So therefore, it is almost constant. So this is our material libraries. Today, we mainly talk about the sponge, but we investigated many materials. FoamSense can be controlled from a few kilopascal to several megapascals. So hardness control range is very wide. So now I'd like to talk about the limitations. So sensible multiple deformation in one carrier is still challenging. It means that we show the demonstration using the multi-pressure sensor, but if we try to measure both, for example, twist and pressure is still very difficult because deformation interfere with each other. So we need to prepare special noise reduction or pattern recognition method for improving this sensor. And material fatigue affects the sensor performance. It's a kind of common problem of soft sensor device. So we need to improvement of material itself or regular calibration method is very important. And third one is precise fabrication is also required. So ink diffused by capillary effect. So it means that we can't separate very small line by line is still difficult. So maybe only 1 cm or 2 cm is a limit for the spatial resonance resolutions. So to cope with this problem, digital fabrication is one possibility. Yes. So now I'd like to show the applications. So the left slide is FoamSense should be applicable to the flexible interface. It is not only on-off sensor device, but also we can detect the continuous motions. So, and center slide it should be very good for apply the wearable device. FoamSense can be made in a body scale, so and not interfere with the human movement. And the right slide, if you use the porous materials, so we just need use conductive ink on these materials. So now he has a spongy sword, and we just add the conductive ink on this black part. Now when he swings the sword, so a sword is bending. Now we can detect that motions. So we just add some conductive ink into the porous materials. So today we introduce new sensor device and its fabrication method, FoamSense. It can measure various deformations. And in the future work, we need to develop the signal processing method, such as noise reduction or pattern recognition for improvement sensor performance. And also, we need to prepare special fabrication process for that. And the last message is device will be dissolved into the materials and be more intelligent. I think material science and fabrication method and signal processing, it includes machine learning, is very critical for this region. Thank you for your attention. So this program is supported by Kawahara Erato project. So thank you for your attention.
Chang Shizhen from Columbia University. Firstly, nice work. I was wondering, have you done any quantitative comparison in terms of accuracy of your measurement? Because you know, applied physics has known that for many of the porous material, the compressibility is highly nonlinear because of some phenomena such as buckling. So it seems this, to me, it seems like accurately measure the compressibility is kind of challenging.
So yes, this sensor is not linear properties. Actually, we don't compare to the signal noise ratio yet. So therefore, the precision is quite limited in the moment. So, but if we measure if we develop the calibration method, it should be more applicable to many applications.
Do you have a sense of the error, like 5% or 10% or?
We only we prepare 3 or 4 sensors by ourselves. Each sensor has a different property actually, but the reaction is almost the same tendency. So it means that if we measure the dynamic range at first, it can be used for in certain type of the sensors.
Thanks.
Yeah, thank you.
Hi, Michael Rivera, Carnegie Mellon University. Yeah. So I've actually done quite a bit of work on piezoresistive, all 3D printed piezoresistive sensors. And I was wondering a couple questions. One is how are you able to get reproducible sensors? So if you have the similar sponge, dip it in the same amount of ink, are you able to get the same response range from it?
So you mean in case of the 3D printing?
Well, in your case, so you were using conductive ink and the piezoresistive effect on the sponge, basically, right?
Yeah, so in case we use a commercially available sponge, so it has, of course, it has a different fold structures, but in total, the performance is very similar. In case of we use the 3D printers, actually it is a bit more difficult than commercial ones because the hole size is a bit larger, so it causes a big difference in the performance.
And so so you mentioned the 3D printed silicone where you dipped it in the ink, but have you considered piezoresistive materials, so conductive clay or ABS? And if you've done any work, do you have any insight on those?
So now I only focusing on the making the carrier structure in the moment, but in the future, so yeah, we also interested in printed out conductive filler itself, or yeah, that must be very good ideas because it's much quicker and more stable, and we can design many types of the sensors.